Hello everyone, welcome to lecture 1 of 3D computer vision, and today I'm going to talk about 2D and 1D projective geometry. Hopefully, by the end of today's lecture, you'll be able to explain the difference between Euclidean and projective geometry. In particular, we'll look at the familiar Cartesian 2D coordinates to describe the Euclidean geometry, and we'll look at how to make use of what we call the homogeneous coordinates to describe the projective geometry. In particular, we'll use homogeneous coordinates to represent points, lines, and conics in the 2D projective space in today's lecture. We'll also look at the duality relationship between lines and points, and conics and dual conics on a 2D plane. Finally, we'll apply the 2D hierarchy of transformation on points, lines, and conics in today's lecture. Of course, I didn't invent any of today's material. I took most of the content of today's lecture from the textbook written by Richard Hartley and Andrew Zieserman, Multiview Geometry in Computer Vision, in particular Chapter 2 for today's lecture. I also took some of the materials from the textbook written by Ma Yi, An Invitation to 3D Vision Chapter 2. I strongly encourage all of you to take a look at these two chapters in the two textbooks after today's lecture to reinforce your idea on today's concept. Projective transformation is actually a part of our life. It's actually a very strong part of our life. And this is because we live in a 3D world where everything follows the Euclidean geometry that can be described as a Cartesian coordinate. But the moment that we open our eye and see the world, we are actually seeing the world through projective transformations. This is because light that is cast on any objects in the 3D world, it's reflected into our eye and it converges into our retina via the concepts of projective transformation. And what's interesting here is that the projective transformation causes geometrical changes to the 3D world that we are living in and the images that is formed in our eye that is sent into our brain. In particular, we can see that from this, for example, in this picture here, we can see that parallel lines in the 3D world. This pairs of lines, it's in fact a parallel line which should not meet in the 3D world that we are living in particular this particular building over here. So what's interesting here is that when it's projected onto an image, it undergone some form of projective transformation, and we can see that the pair of lines, they actually meet at a certain point here, at a finite point in the image. This is the same thing when we are looking at the scene via our eye, because our eyes are actually the most powerful form of cameras that is available, and it functions the same way in this particular case here, where I have a digital camera where the lights are projected into the photo sensors in my camera over here, and we can further see that rectangles that are in the real world scene, for example the window over here, because of the projective transformation, when the light ray is being projected from the scene into the camera, we can see that the windows that is being formed on the image they are no longer rectangles over here. In fact, it becomes some form of parallelogram over here. And another example here would be the circle, this clock over here, this clock face over here. In the 3D world, in the Euclidean world that we're living in, it's actually a perfect circle. But when it is projected onto the image after projective transformation, we can see that the geometry circle is not preserved. It becomes an ellipse in this case over here. And we saw from the previous slide that certain geometrical properties, they are not preserved by projective transformation. In particular, we saw 3 examples. A circle may not appear as a circle anymore. It becomes an ellipse, and a parallel line, they will not they will not stay parallel. They actually meet at a certain finite point when it is being projected into the image, and as well as a rectangle may appear as a parallelogram when it's undergone some form of projective transformation. And in fact, if a closer look at the images or a closer look at the world through our eyes, it's not difficult to realize that in fact, the angles, the distance, and the ratio of distances are all not preserved. For example, in this case here, I have two parallel lines in the scene. These are supposed to not form any angle at all, but when it's projected onto the image, you can see that this is what is going to happen. It's going to meet at a certain point and it's going to form some angle. Even lines that are not parallel, for example, they already form some angle of theta over here. When it's being projected onto an image, we can see that this angle of theta, it can actually change to theta prime, which is not the same as what you see, what it really exists in the 3D world. And the distance here could refer to the distance between 2 points, two real points in the 3D world. So suppose that this distance here is denoted by d over here. When it's projected onto an image, we can see that this d over here, between these 2 points, it becomes d prime. They will never be the same, or it's unlikely that they are going to be the same. As well as the distance between the two endpoints of a line, or the perpendicular distance of two lines. Suppose that I'm looking at this distance denoted by d over here, that's formed by two lines, and the projection to an image would cause this d over here to change into d prime, for example. As well as the ratio of the distances. Suppose that I have two distances that is formed by these 4 points over here. Let's call this D1 and this D2 over here. And the ratio between these two distances is denoted by D2 over D1 in the 3D world. But when it is projected onto an image, we can see that this D1 becomes D1 prime and D2 here becomes D2 prime. That means that D2 prime and D1 prime will not be equals to the ratio of D2 and D1 due to the effect of projective transformation. We shall see that all this analysis, all this mathematical or geometrical analysis can be formalized using the homogeneous coordinates that we are going to learn in a while. So we've seen earlier that most of the geometrical property changes when it undergoes some form of projective transformation. So the question here would be to ask ourselves on what's a good way to quantify, or what's a good way to study this projective transformation. Fortunately, a property that is preserved in projective transformation is what we call the straightness property. And this becomes the most general requirement on the projective transformation. In other words, we say that the straight line or straightness property stays invariant after certain form of after the projective transformation. We can see from the image earlier on that in that case, any straight line in the scene is actually still projected into a straight line after it has undergone some form of projective transformation, despite that the angle, the ratio of the distance and the distance may change, but the straight line will still remain as a straight line after some form of projective transformation. And the thought here is that we may actually make use of this invariant property of the straightness to define a projective transformation, or to describe the whole set of projective geometry that preserves the straight line. This means that mathematically we can formulate some form of projective mapping, or some form of mapping that maps from one projective space. So this is a projective space that maps from one projective space to another projective space over here. For example, in the 2D projective space, which I'm going to denote as P2 over here. So, but in this case over here, since we observe that straightness is being preserved, what it means is that we want to define a projective transformation, which I now call temporarily as H over here, that maps any straight lines in one of the scene into another scene, such that the straightness property here will also be preserved. And more generally, we'll study the geometric properties that are invariant with respect to projective transformations in projective geometry. So straightness or straight lines, preservation of the straightness in the projective transformation is one of the property. We'll throughout these lectures, we'll look at some other form of invariance, geometrical invariance that are invariant to certain form of projective transformation in projective geometry. So far, what we are familiar with in geometry is what we call the Euclidean geometry. And this is an example of a syntactic geometry that we all have learned since our primary school days when we are taught geometry and mathematics. This is also making use of what we call the axiomatic methods and its related tools to describe geometry or to solve any problems in geometry. For example, if I want to solve the a triangle, a right angle triangle, and I solve the angle over here, we can make use of compass and rulers to actually solve this particular problem. We can measure the angles between any two lines in this triangle using a compass, or we can just simply measure the distance of this triangle, the edges of this triangle, using a ruler and compute the angle using the cosine rule or the sine rule. So this is the most standard form of Euclidean geometry that every one of us learned in school. And in fact, Euclidean geometry has also a very long history. It was actually invented by the Greeks in very early days, as depicted in this particular painting over here by Raphael in the 1500s. We can see that in this painting over here, there's a group of philosopher, or there's a group of mathematicians trying to solve some form of Euclidean geometry problem by making use of the compass and the straight edge to solve this particular problem. And what we're going to look at in this module over here is what we call the projective geometry. And instead of making use of axiomatic methods and the related tools such as compass and straight edges to solve the problem, we're going to make use of mathematics. We are going to make use of coordinates, and in particular algebra or linear algebra to solve problems in projective geometry. And we can see that we will learn in the later part of the lectures how we can convert projective geometry representation, in particular homogeneous coordinates, into the Euclidean geometry or the Euclidean space. So Euclidean space are usually represented by the Cartesian coordinates. And the what we call projective geometry, since it's making use of math and coordinates and linear algebra to describe projective geometry and to solve problems in projective geometry, we'll call this also the analytical geometry. We shall see that one of the most important results from projective geometry is that the geometry at infinity can be nicely represented. So in Euclidean space, there's no way to represent any points that occurs at infinity, or any lines that occur at infinity, or any planes that occurs at infinity. And in fact, the seemingly only way to represent this lines, point, or planes at infinity in Euclidean geometry is to make use of the infinity representation itself, which ends out to be an exceptional case in mathematics. When we do any mathematics operations, infinity it's often unrepresented, or it ends out to be a exceptional case in Euclidean geometry. But we'll see that by making use of homogeneous coordinates in projective geometry, the infinite points, lines, and planes can be represented elegantly using just a set of numbers, where we do not need to treat them as a separate case. So we'll make use of homogeneous coordinates to describe the projective space. As we have learned in our high school mathematics or geometry, that in the Euclidean space, which we denote as E over here, can be easily represented by a set of Cartesian coordinates, which are living in the real number space. So for example, in the 2D space, 2D Euclidean space, this is usually represented using 2D real numbers in the Cartesian coordinates, as compared to in the projective space. In this case over here, if we are talking about the 2D projective space, then this would be represented by a set of homogeneous coordinates, which are a set of three numbers. They are also taking a form of real numbers, but in this case, this will be in the R3 space, where we are talking about three numbers over here. We'll see that a point in the homogeneous coordinates can be represented with using these three numbers, kx, ky, and k respectively. So these three numbers over here, it forms a point in the homogeneous coordinate, or it represents a point in a homogeneous coordinate that corresponds to kx divided by k and ky divided by k, where k over here can be cancelled off to get x and y in the Cartesian coordinate. So here in this particular statement over here, what we have seen is that given a homogeneous coordinate, we can easily convert it back into the Euclidean space or into the Cartesian coordinates over here by simply dividing the first two coordinates of the homogeneous coordinates with the last entry in the homogeneous coordinates over here. And it's also interesting to note that kx, ky, and k is equivalent for all forms of k. So we can think of it this way, that the k here is just a scalar value that is multiplied by the homogeneous coordinates of x, y, and 1 over here. So for all k's over here, this particular representation of homogeneous coordinates represents the same point of x and y in the Cartesian coordinate space. Now, we can also use the homogeneous coordinates representation, these three numbers, to represent a point at infinity, a 2D point at infinity, by simply setting the third value here, k, to be equals to 0. And we can see that this is an elegant form of representing points or 2D points at infinity, because it doesn't require the exceptional representation of infinity or the concept of infinity over here. All we need to do is just to set the last value over here, k, to be equals to 0. And we can see this clearly when we convert this set of points over here, this homogeneous coordinate x, y, and 0 over here, into the Cartesian coordinates by simply dividing x over 0 and y over 0, following the rules that we have seen earlier in the first statement over here. And this will end out to be infinity, infinity, where in the Cartesian space, which actually represents a point at infinity. But it's actually very inconvenient to represent infinity in the Cartesian coordinates directly. So here, homogeneous coordinates offers us a more elegant way of representing points at infinity. And generally, the Rn Euclidean space can be extended to a Pn projective space as homogeneous vectors. As we will see in this particular lecture, we can see that this example over here for a point, we can see that for a Euclidean space of R2 represented by R2 space, it can be actually extended to a projective space of P2 easily by just dividing the values of k, the third coordinates here, and we can easily convert Euclidean space to projective space and vice versa. We will see in the next lecture that this can also be done in the R3 space with some difference from exceptional properties that we will see that arise from a higher dimensional space over here compared to the 2D space, in particular the hierarchy of transformation. And pictorically, we can see that the homogeneous coordinates, a point in the homogeneous coordinate, can actually be represented by a ray as shown in this diagram over here. So as what we have mentioned earlier on, that any points on the homogeneous coordinates can be represented by these three numbers over here, kx, ky, as well as k over here. And this k is a scalar value that is multiplied by x, y, and 1 over here, where for any k or for all the k's, this over here, these three numbers over here would be the same 2D point in the Cartesian space. And what we can see here is that in this case here, since k over here is a scale, what this means is that x, y, and 1, and 2x, 2y, and 2, as well as all the way until k, x, k, y, and k, they all represent the same point. And if we were to join all these points together, we can see that it actually forms a projection. It actually forms a ray that joins out all these points over here that represents the same 2D point in the Cartesian space. And hence, we can see that we can conclude that the homogeneous coordinates of a point or representation of a point is actually equivalent to a ray over here if we were to plot it out in the Cartesian space of XYZ coordinates over here. So we can also look at another example over here. Suppose that there's another point over here which is actually given by kx prime, ky prime, as well as k over here. We can see that this particular point is equivalent to, on this particular plane over here, is equivalent to 2x prime, 2y prime, as well as 2 over here. And there's also a corresponding point of x prime, y prime, as well as 1 over here. So if we were to join all these 3 points up, then this will form a light ray that passes through all the sets of points. And it's also interesting to note that it's not necessary that k takes an integer value. So k need not be just an integer value of 1, 2, 3, 4, and so on and so forth. It can actually be any real number. So k over here can actually be any real number where it can actually be equals to 1.1 or 1.23 and so on and so forth. And in this diagram over here, we can also see that based on our definition of a point at infinity, it was given by x, y, and 0 as defined in the previous slide over here, where x and y can take any value. So what this means is that all the points that are, or any vectors on this that is lying on the xy plane, over here, they all corresponds to points at infinity. And we will also look at the what we call the line at infinity, which we will represent it as L infinity later on, that this is actually equals to 0, 0, 1. We'll see how to derive this particular representation in a few slides time. And what's interesting here is that this L infinity is actually corresponding to any point on the z-axis over here, since it's 0, 0, 1. And it's interesting to note that the origin of the Cartesian coordinate of 0, 0, 0 over here is undefined. So this point is actually undefined in homogeneous coordinates. We do not use this representation at all in homogeneous coordinate. So we'll now look at the homogeneous notation for lines on a plane, which means that we are looking at the 2D line and the incidence relations between the lines and the points, which we will also, from here, we will also look at how to derive the duality relation between lines and point. We will realize that the lines and the point representation on homogeneous coordinates are actually interchangeable. And in the pictorial form that we have seen earlier, we saw that a point in the homogeneous coordinate is actually represented by a ray, represented as 3 numbers, kx, ky, and k, where it's going to be the same for all k's. That's why the point is actually represented as a ray in the projective space in the homogeneous coordinates. And we'll see that a line on a plane, a 2D line on a plane over here, which we denote as L over here, it actually is represented by a plane because it projects to become a plane in the 2D projective space. And in this case here, we can see that a plane can be represented by its normal vector. So what happens here is that line, the representation of line, geometrically, it's actually represented by the normal vector of the plane that is projected from this particular line over here. Now we all know that a line in a plane, which is a 2D line, can be represented as this particular polynomial equation over here, ax plus by plus c equals to 0. This simply represents a line in the xy plane in the Cartesian coordinate, and this is the equation of ax plus by plus c. Or if we were to manipulate this particular equation a little bit, we can see that this simply becomes y equals to minus a divided by bx minus c, or simply y equals to mx plus c, which is the familiar equation of lines that we all have learned throughout our high school mathematics or even junior high school mathematics. And we know that the different choices of the parameters of x, y, or the coefficients of x, y, which is a, b, and c, will give rise to different lines, because a and b here controls the gradient uh, of this line, on how steep this line will be on the xy plane over here, and c here would be the intersection of the line with our y-axis over here. Thus, a line can be represented naturally by the vector, these three numbers a, b, and c, without having the need to concern about x and y over here. And hence, in homogeneous coordinate representation of lines, we'll just simply make use of the coefficients to the line equation over here in 2D, a, b, and c, to represent the lines in homogeneous coordinates. So we can see that there is a similarity in the representation with the homogeneous coordinates of points, which is also represented by three numbers over here. And but physically or geometrically, it actually means different things. So in the case of the lines, or in the case of the points, is kx, ky, and k over here, and this is actually representing all the points that are in the array that is formed by the projection onto the origin, and the intersection with all these planes over here, which determines the k value, would determine the point in the Cartesian coordinate. And in this case here, the line is also represented by a 3 number, but in this case, a, b, and c over here simply represents the coefficient of the lines. And it's important to note that the correspondence between the homogeneous representation of a line as A, B, C, a 3 vector of A, B, C here, is not there's no one-to-one correspondence between this homogeneous representation and the usual vectors that we known of in the Cartesian space of A, B, and C transpose over here. This is because the lines are represented by this polynomial equation of ax plus by plus c equals to 0. And we can see that in the homogeneous representation, or in the line representation, this polynomial equation over here, when multiplied by a scalar value of k over here, it's going to be the same line. It's going to represent the same line, because this k here can be simply factorized out into k multiplied by ax plus by plus c equals to 0, and this k can be cancelled off. So regardless of the value of k here, it's always going to represent the same line. But in the case of a vector, if we were to write the vector as ka, kb, and kc here, these are going to represent the different lines or different vectors, different 3 vectors in the Cartesian space for different values of k. But in this case here, in the homogeneous representation here, we say that a, b, c, the 3 vector of a, b, c, and the 3 vector of k, a, b, and c transpose represents the same line for any non-zero k, and therefore what this means is that they are equivalent class. And note that the vector of 0, 0, 0, as I've mentioned earlier, when we look at the diagram that represents the projective transformation, the projective space, it does not correspond to any line neither does it correspond to any point at all. So this is what we call the singular point, where it doesn't represent anything at all in the homogeneous coordinate. Now we'll see the incidence relation. So incidence relation means that how a point and a line coincide or intersects with each other. So in this case here, it would be a line, and we will look at the relation or the mathematical formulation in homogeneous coordinates form on how to represent the incidence relation where a point sits on a line. The point, let's denote it as x, and the line, let's denote it as L, which is given by these two values over here. And we say that a point lies on a line if and only if it fulfills this particular equation in the Cartesian space. This is the equation, the line equation that we all are familiar with in Cartesian space. And in fact, A, B, and C here represents the parameters or the coefficients of the line, and X and Y here simply represent all the points that are in this line when we plot it out in the Cartesian space of X and Y over here. So we can rewrite this form of equation, the polynomial equation, into a matrix multiplication or a vector dot product over here. We can see that it becomes xy1 multiplied by a, b, and c transpose. And interestingly, this x and y and 1 over here, it becomes the homogeneous representation, the homogeneous coordinates of a point x, y in the Cartesian space. And a, b, c transpose over here simply coincide with what we have defined earlier to be the homogeneous coordinates of a line represented by L. Hence, we can simply rewrite this into xy1 multiplied by L, which is the vector, the 3 vector that represents the line. And according to this particular polynomial equation that represents the line, we can equate this product over here to be equals to 0. So similarly, for any constant non-zero k, this relation, the incidence relation, will always hold true. And in this case here, we can say that for any point represented as the homogeneous coordinate kx, ky, and k multiplied by a, b, and c, it will always gives us 0 over here. So it's going to be the same even if we were to scale L as what we have seen earlier, that this is going to be scaled by another scale where we can factorize out, say for example k prime. So we can see that k and k prime are going to cancel out when we equate it to 0, and at the end of the day, it's still this particular equation that represents the incidence relation between a point and a line. Hence, the representation that we have described earlier of kx, ky, and k in 2D, in the projective 2D space for varying k value, is a valid representation of a point which is in the Cartesian coordinate space. And this actually also proves that, or it actually shows the validity of our definition of the point in the projective space using homogeneous coordinates. And we can see formally this would be the representation of any point in the homogeneous 2D space, x1, x2, and x3, a 3 vector over here. And we say that it's in a 2D projective space, which is equivalent to the Cartesian coordinates of x1 divided by 3 and x2 divided by 3 transpose in the Cartesian coordinate space. So in this case here, this is our projective space, and this is our Cartesian coordinate space. More formally, the point x lies on the line if and only if the dot product of the point and the line is equals to 0, as what we have seen earlier. So this dot product over here simply expressed out to be ax plus by plus c equals to 0, and we simply factorize this into a dot product as written in this former form over here. So this is the first example that we see that how linear algebra, because this is the dot product is from linear algebra, how linear algebra can be used to describe the incidence relationship between a point and a line in the projective 2D space. And note that the expression of X transpose L is just the inner or scalar product, or simply called the dot product, as I've mentioned several times. And the dot product is equivalent regardless of how we sort the order of this X and L over here, because we can simply see that you will still evaluate into this form over here. And we shall see later that because of this swapping over here, we can and the same representation with the free vector for a point and a line in the 2D projective space. Hence, we can see that the role of the point and a line can be interchanged, which we'll look at in more detail when we talk about the duality relationship. And now, the degrees of freedoms of a point is 2 degrees, simply because we saw that there's x and y coordinates where it can be changed. X and y respectively has 1 degree of freedom, and a line also has 2 degree of freedom in the 2D projective space, because there are 2 independent ratios of A is to B is to C, and this can actually be made more clear when we by the example that I've shown earlier, that we can actually rewrite AX plus BY plus C equals to 0 into Y equals to minus B or A divided by BX minus C, which is simply equals to MX plus C. So in this case here, we can see that there are only 2 parameters that matters, which is M and C, which is the gradient and the Y intersection of the line. So M over here is actually formed by the ratio. So it should be B divided by C over here. So because B is a coefficient of Y, and it should be also divided, C should also be divided by B. So we can see that in this case here, it's the ratio that matters, A divided by B and C divided by B, that matters in the line. Hence, a line also has 2 degrees of freedom in the projective 2D space. Now, the intersection of 2 lines in the 2D space will always give rise to a point, because any 2 lines are always going to meet at a certain point, and we will see that this includes parallel lines, which we will assume that they or mathematically define them to intersect at infinity, at a point at infinity. And the formally, using the homogeneous coordinates representation, 2 points always, or 2 lines always intersect at a point, would be given by the cross product of 2 lines. Suppose that we have 2 lines, L and L prime. The intersection, which we denote as X over here, would be given by the cross product of L cross by L prime over here. And geometrically, we can see that since I have mentioned earlier by showing the diagram that line L in projective space is actually represented by a plane, because it projects to a plane, and all the lines on this plane actually represent all the parallel lines in this plane that lies on this plane. It actually represents the same line because of the regular scaling that can be cancelled out, as what we have, as I mentioned earlier, that K AX plus BY plus C must be equals to 0, and K here doesn't matter. And we can see that if we were to have 2 lines which we denote as L and L prime over here, they both back project to a plane. And what's interesting here is that on the 2D line, on the these 2 are 2D lines, and on the 2D plane, the intersection of these 2 lines will always be at a point over here, which actually in the homogeneous representation, homogeneous coordinate representation, is denoted by this ray over here. So what this means is that the cross product, when we take the cross product of these 2 lines over here, we will get this point, and in a homogeneous coordinate, this is equivalent to this particular ray or vector over here, the 3 vector that we use to represent the homogeneous coordinate. And a further description of this would be that the line here, the geometric intuition of the line, since it back projects to a plane, we can also see it as the vector over here, the normal vector of these 2 planes respectively, that represents the line of L and L prime over here, and the cross product using the right hand rule over here, the cross product of these 2 vector actually gives a octagonal vector that is in this direction over here, which is directly corresponds to the point of x. Hence, a point is actually given by the cross product of the two line L and L prime respectively. Here's a mathematical proof on how this cross product works. Just now I have given you the geometric intuition behind why a point is represented as the cross product of two lines L1 and L prime. Now I'm going to give you a mathematical proof. Now, suppose that we are given two lines L, which is represented as A, B, C, and A prime, B prime, and C. The triplet scalar product identity gives this. The triplet product scalar product identity, it simply means that the dot product of the cross product of two lines are going to be 0, which we can see that the cross product actually of two vectors, which we denote as L and L prime over here, is going to be the line that is going to be the vector that we denote by V over here. This guy here is going to be L cross L prime over here, and this is going to be octagonal to each other. All these three lines, they are all going to form. They are going to be perpendicular to each other. So what this means is that if we take the cross product of L and L prime, we will get V, which is octagonal to L and L prime. And if we were to take the dot product of V with any one of these lines, L or L prime over here, since they are 90 degrees apart, the dot product of these two are going to be equals to 0, because dot product is simply if I have two lines and I take the dot product, or two vectors, I take the dot product. The dot product is going to give me AB cosine theta equals to A dot with B. The dot product of A and B is going to give me this. So in the case where A and B are perpendicular to each other, a vector of A and B, they are perpendicular to each other. What this means is that the angle between them is going to be 90 degrees. Hence, the cosine of 90 degrees is going to give me a 0 over here. Hence, this is going to give me a 0 of the relationship over here. And if X is taught as the representing point, then X lies on both lines L and L prime. Hence, it is the intersection of the two lines over here. So we can see that because of this relation over here, the triple scalar product identity over here, this relation is going to give rise to 0. So we can replace L and the cross product of L and L prime here with X over here in the first case here. And we can also see that this guy over here can also be denoted as X. Hence, if we put this into the this particular equation here, we can see that from our earlier definition, the incidence relation of X and L, the point and a line, when a point lies on a line, it has to give a dot product of 0. This is arising from the equation of the line that we have seen earlier. Hence, we can replace the cross product of L and L prime to be X, where we can conclude that the cross product of two lines is actually equals to the point itself. And this is the algebraic derivation of the intersection of two lines that gives rise to a point. And conversely, we can also see that the cross product of 2 points, X and X prime over here, gives rise to a line L. We can see this, or we can observe this geometrically using this representation in the diagram over here. So we have seen that 2 points is actually, it can be represented as 2 rays in the homogeneous coordinates, for example, X and X prime over here. And the cross product of these two lines, since they lie on the same plane, it's going to give rise to a perpendicular vector, a perpendicular normal vector over here, which we denote as L over here. And this L would represents this particular plane over here that intersects the plane K over here at the line represented by L. Hence, we say that the cross product of X and X prime it's going to give rise to a line, a vector that represents the line in the homogeneous coordinates form. And algebraically, the proof is given by this. Suppose that we are given 2 points x and x prime. The triple product identity will use the same trick of the triple scalar product identity. It gives x dot with the x cross x prime over here is going to be 0, as well as x prime dot product with x cross x prime is also going to be 0, which we can rewrite this here, this part over here, since the cross product is going to give another vector, a 3 vector, which we can rewrite this as L, and this part over here as L2. So and we can see that this is exactly the incidence relationship between a point and a line, which we have mentioned earlier on. And here we can simply write L to be equals to x cross x prime. Hence, we can conclude that the cross product of 2 points in the homogeneous coordinates give rise to a 3-vector line in the homogeneous coordinate. And we can also see that there's no exception to be made of the intersection of 2 parallel lines. So in Cartesian coordinates, this would become problematic, the intersection of 2 parallel lines, because there is no way to represent this intersection in the Cartesian coordinates, as they simply do not intersect, or they actually intersect at infinity. So there is no way of representing infinity. We'll end up to have a division by 0, which would be not solvable in Cartesian coordinates. But in the homogeneous representation, we can see that this becomes elegant to represent. So now let's consider 2 parallel lines, ax plus by plus c equals to 0, as well as ax plus by plus c prime equals to 0, which we represent in the homogeneous coordinate as abc and abc prime over here. So we can see that since I mentioned that we can rewrite these equations into y equals to a over b minus a b x minus c over b into the form of y equals to mx plus c. So we can see that since a, b in these two are the same, and this means that in this case here they are the gradient, which means that there are 2 parallel lines which simply intersects at a different point, c and c prime respectively. And hence, from a geometry or from a Cartesian point of view, we can easily tell that if the 2 numbers of the lines are the same, then these 2 lines are parallel to each other. And the intersection of the 2 lines L and M prime, which we have seen in the previous slide, is given by the cross product of L and L prime. And this can be evaluated in this particular form over here, where we will simply get a scalar value of c prime minus c multiplied by the 3 vector that represents a point or a homogeneous point in the projective space. And in this case here, the third number here, it's always going to be 0. And when we ignore the scale factor, we can simply represent the point, the intersecting point at b minus a and 0 over here. Hence, what this implies is that this is actually the intersection of the 2 parallel lines, and it actually algebraically we can actually see that this point actually is the point at infinity, which means that 2 parallel lines actually intersects at the point of infinity, which can be represented very elegantly using homogeneous coordinates, since the last value over here is 0. When we convert this back into the Cartesian coordinate, we will get b divided by 0 minus a divided by 0, which is simply infinity and infinity that represents a point at infinity. Now, example here is that consider 2 lines x equals to 1 and x equals to 2 over here. So in the geometrical way, these are actually 2 lines parallel to each other at x equals to 1 and x equals to 2 over here. And these 2 lines are parallel, and we will see that it consequently will intersect at infinity. So using this Cartesian representation over here, there's no way of finding the intersection over here, or representing it elegantly using mathematics. But in homogeneous form, we'll see that, or we have already seen the derivation that this can be done in an elegant way. So the two lines over here can be represented as L equals to -1, 0, and 1 over here, and and as well as -1, 0, and 2 over here, which represents this particular two lines, and their intersection point can be given by the cross product of these two lines over here, which is simply ends up to be 0, 1, and 0. We see the last coordinate is 0. This means that this point is actually a point at infinity in the y direction, because 0 represents x and 1 represents y, which means that this vector over here, this point here, is pointing towards infinity, and that's in the y direction, which can be verified over here, that since these two lines are parallel in the y direction, they must intersect at infinity in the y direction. So we have seen in the earlier example that any two parallel lines denoted by A, B, C, and A, B, and C prime intersects at a point at infinity, which is given by the ideal point of B minus A and 0 for all the C's. And hence, we also have seen that the ideal points will lie at the line at infinity. So this is the line at infinity. The ideal point is going to lie on this line at infinity. And hence, we can conclude that any two parallel line is always going to intersect at a ideal point at infinity, which is going to be lying at the line at infinity. Hence, any two lines, parallel lines, is going to intersect the line at infinity at the ideal point. And we have also seen that the ideal point is actually the direction of it can be seen as a directional vector along the intersection of these two parallel lines. In other words, B minus A over here can be seen as the tangent to the line, which is the direction of the line that is pointing towards the point at infinity, which is B and minus A over here. And the orthogonal to this line, the tangent direction vector, would be the normal of this line over here, can be given by A and B over here. And we can verify that these two are tangent to each other, or orthogonal to each other, B minus A and A B transpose over here, by simply taking the dot product of these two guys. We can see that it will give us AB minus BA, and that's going to be equals to 0, the dot product of these two. And I have said earlier that the dot product of any two orthogonal vectors A and B is going to end up to be 0, which indeed verify that these two are the tangent to the line as well as the normal to the line. And what's interesting here is that as the direction, the line direction, the parallel line direction varies, A and B varies, we can see that the ideal point that intersects at the line at infinity is going to also vary along the line at infinity, since these two parallel lines are always going to intersect the line at infinity. But what it means here is that with the change of the direction of the lines, the parallel lines, the intersection at infinity is going to vary, and this simply means that the tangent, the direction of these lines, parallel lines, is going to change with A and B. Hence, the line at infinity can be thought of a set of directions of the lines in the plane, since all these are going to live in the 2D plane. Now, through the dot product, we can see, or through the incidence relation of that is denoted as the dot product, we can see that the row of points and lines, since they are all three vectors over here, it can be interchangeable in the incidence equation in the dot product. And the intersection of the two lines and the line through 2 points can also be interchangeable, using the cross product over here. So this leads to the observation of the duality principle, which simply means that the point and the line, they are dual to each other in terms of homogeneous coordinates representation and the operations in the projective space. And the duality principle simply means that any theorem of two-dimensional projective space, there exists a corresponding dual theorem that may be derived by interchanging the rows of the points and the lines in the original theorem. So what this means here is that in the context of these guys over here, what it means is that as long as we prove the cross product of two lines gives rise to a point, there is no need for us to prove on the other hand, where 2 points, the cross product of 2 points will give us a line. This is because due to the duality principle where line and points are interchangeable, we simply just need to prove any one of this for the other one to hold true.